Thanks a lot, Amina, for the kind introduction. I'm very excited to be here. Hi, everyone. Today, I'll be talking about a problem in the space of storage systems. So this is a problem motivated by increasing efficiency in storage systems, which we call as code conversion. And then I'll talk about a theoretical framework called convertible codes to study this problem and to address the problem that I will introduce soon. So I'll have so this is the outline for today's talk. I'll start with an introduction and motivation for the problem of code conversion. And this would be motivated from real systems, measurements, and traces. And then I'll talk about convertible codes, the theoretical framework, and a family of codes to address the problem of code conversion. And then I'll talk about two specific metrics in which we will study this problem and design codes and analyze the performance. And then I'll end with a summary and a discussion on open problems. So large-scale cluster storage systems typically comprise of millions of disks and also store petabytes to exabytes of data today. And these systems are typically incrementally built according to design, as the demand increases. And hence, there is a lot of heterogeneity in the disks that comprise these systems. And this heterogeneity is both in terms of make models, which corresponds to basically which is the which manufacturer and which type of disk and which model, and also the age of the disk. And it is well known that in these large-scale storage systems, failures are common. And these failures are measured using a metric called as annualized failure rate, or AFR in short. And AFR basically stands for expected fraction in percentage of disk failures in a year. And then in these large-scale storage systems, in order to prevent data loss due to these failures, erasure coding is typically employed in order to add redundancy for fault tolerance purposes. Now, just a quick recap on erasure codes and how that get used in the context of storage systems. So erasure codes are basically mathematical tools for adding redundancy in a resource-efficient way. So basically, when we talk about an erasure code, we will be considering two parameters, N and K. An NK erasure code encodes K messages. So in this picture, we have this unshaded box as the K message symbols, which would be the raw data that we want to store or encode. And then this NK code would encode this data and generate N code symbols. And these N code symbols together is called as a code word. And these code symbols are some mathematical functions of the original message symbols. And these mathematical operations are performed over some modular arithmetic, for example, over finite fields. And these parameters, N and K, are called as length and dimension, respectively. And in this picture, I've shown the N code symbols separated into two parts, where there are K symbols first, which are unshaded, and then there are N minus K coded symbols, right? So such a code word or such a code is called as a systematic code. Basically here, out of the N code symbols, we have the original K message symbols intact in uncoded form, which is the first K symbols here, right? And the remaining N minus K are the redundancy that is added, and they are called as the parity symbols. So in a systematic code, we basically have the original data, which would be the K message symbols as is. And then we will be adding N minus K parity symbols. And these parity symbols are some mathematical functions of the original message symbols. And the simplest example to consider as a toy example would be just a single parity, which would be XOR of the original message symbols. Okay, that's just a toy example to keep in. Okay. So now, when designing these codes, so these are designed to meet certain decodability requirements. And one very common decodability requirement that is used in storage systems is called as maximum distance separable, or MDS. which basically means that out of these n code symbols, any k are sufficient to decode the original data. So basically, if we have any k out of these n, the data is intact, that is, data is not lost. So out of these n code symbols, we can tolerate loss of any n minus k. So basically, an nk MBS code provides fault tolerance to any n minus k code symbols being lost. And then one last point in this recap is that we will be focusing primarily on linear codes. Again, almost all codes employed in storage systems and in general in other systems also are linear. And linear codes are basically codes where the code word symbols that I just talked about, which are mathematical functions of the original message symbols, right? And those mathematical functions are basically linear combinations. So since they are linear combinations, now the entire code can be specified as a matrix of these linear combinations, and that matrix is called a generator matrix. So a linear code, an nk linear code, will have a generator matrix of size k by n. So you will multiply the matrix with the vector k original message symbols, or the generator matrix. It takes the linear combinations and it will give the code symbols. So for a systematic code, we know that original message symbols are intact in the first k symbols, right? So the generator matrix then would be of this form. There will be an identity matrix I and then a parity matrix P. And this parity matrix P would specify the linear combinations for the parity symbols. Okay, so now this was just a very quick refresher on Erasure codes. Now let's see how this gets used in storage systems. So I'm taking this example of a n equal to 14, k equal to 10 code. So this is an example drawn from an Erasure code, which was employed in Facebook's data analytics cluster on almost petabyte-sized data. Okay, so now how does this code get employed in distributed storage systems? So now since k equal to 10 in this example, we start with 10 data blocks. So here we have A to J. And then since n is 14 and k is 10, n minus k is 4. That is, we have 4 parities, right? So we have these 10 data blocks and we create 4 parity blocks. And these parity blocks, as we just discussed, are some mathematical functions of the original data blocks. And then each of these 14 blocks are then stored on different disks on different servers, and typically also chosen from different failure domains, for example, power domains and so on, so that they are all on different failure domains. And now since this is an nk code, and you can tolerate any n minus k failures, right? So now basically this is how a storage system that uses erasure coding gets its fault tolerance. Okay, so now given this context that we have nk erasure codes and how they get employed in storage systems, now let's see how these parameters n and k get chosen and what it means for the system. Now in storage systems, the amount of redundancy that gets added to the system is a function of these parameters n and k. So for example, if we consider the same example of n equal to 14, k equal to 10 code, the storage space overhead is 40%, which is basically you need 1.4x storage space, which is n over k, right? So in order to store the data, that is, if you have 10 petabytes of data, you need 14 petabytes of actual physical storage space because we are adding this redundancy, right? So now this redundancy is very important because it comes at a significant cost to the system administrators and system operation because it requires additional hardware, and also it increases the energy consumption and operational costs of physical space, cooling, and just the people involved and so on. It turns out that this cost is so significant because of the scale of these systems that reduction of even single-digit percentages in terms of this storage space overhead is significant, and industries and the companies involved here are interested in investing in engineering efforts, even if the reduction is just a single-digit percentage. So it's that significant, primarily because of the scale of these systems. Okay, so now we've seen the role of erasure codes in storage systems and how they add redundancy and what is its impact. Now let's see how these parameters are chosen. So currently, these parameters are chosen in order to meet durability and availability requirements using some metrics, for example, considering mean time to data loss, and also reconstruction constraints. That is, when a particular node in the system is down, how much time does it take to reconstruct it because that data is unavailable, or you have to reconstruct it on the fly until it comes back, which would have basically higher latency in responses. So taking all these things into account, these parameters N and K are chosen based on an average failure rate consideration across the disk fleet. That is, this gets chosen in a top-down fashion, and it's agnostic to where the data actually gets stored. So in essence, it is basically agnostic to how the failure rates vary or among the disks that are in the system. So implicitly, this is assuming that the disks fail similarly. So we did a study on the failure rate of disk drives on millions of production disks at Google, NetApp, and Backblaze. Backblaze is a data backup company, which I think went IPO just a couple of days ago. And so in our study, we observed that failure rates vary significantly. So I'll show a plot here. In this plot on the y-axis, we have the AFR, and on the x-axis is the make model. So this is a bar chart with a box plot where each of the boxes here is a make model. So we have more than 60 make models. And basically what we saw is that there is an orders of magnitude difference in the AFR across different make models. And AFR varies not only across make models, but it also varies over time with the age of the disks. So this is a well-known disk hazard, or sometimes also called as a bathtub curve. So this is a textbook curve where, again, we have AFR on the y-axis and age of the disk on the x-axis. And as we can see, AFR decreases initially, which is called as infancy, and then it is pretty stable and low in between. It's called as a useful life period, and then it increases again in what is called as wear out period. Now on the right here, I'll show what we observed, and it matches with what we see here on the left. So this is from the production data on the right here. And again, we see similar variation in this bathtub fashion across time, that is with the age of the disk. So AFR varies significantly across different make models and also over time with age. So this opens up this opportunity for tuning the amount of redundancy to the observed failure rates, especially during this useful life period in between, where the AFR is low and it is pretty stable. So now in this period, we can lower the redundancy and hence lower the storage cost. So we proposed this idea and made a case based on the study of production data in our work in FAST 2019, which is a storage systems conference. And from evaluations on data from production clusters, we show that there is a potential for 10 to 15% more than that in these storage systems, which are already erasure coded, which means they're already optimized, right? And then this translates, as I was mentioning earlier, even these modestly looking savings, because of the size of the systems, translates to huge and significant benefits. For example, in production storage systems, this literally translates to millions of dollars of reduction in the operating costs. Okay, so it looks like redundancy tuning has a potential for significant improvements. However, redundancy tuning is not free. Okay? So when AFR of a group of disks change over time, now we need to change the rate of the erasure code that is used to encode the data that are stored on it. right? Because we have to tune the redundancy, right? Now, often this requires changing both the parameters n and k of the code. It's easier if we can keep the dimension, that is k, fixed and increase or decrease just n. And there are ways to do it efficiently. But it turns out that because of the other constraints on the system, often you need to change both n and k. Okay, so the default approach for doing such a conversion is to re-encode the data. That is basically you read the original data, generate the new parities, and then store it again. Okay. So this requires basically reading all the original data units and writing the new ones, right? So which turns out to be prohibitively high cost for the system because you are reading the data again, so it consumes I/O, you're transferring across the network, consumes bandwidth, and this interferes with the foreground operations. Okay, so, and typically a large number of disks undergo transition at the same time, and hence this results in a very spiky and highly varying resource consumption. So I'll show you what it looks like on a production system. So this is data drawn from traces from production clusters at Google, and what would it look like if we do redundancy tuning on them. So on the y-axis here, we have total I/O consumed per day, and x-axis is different date. And as we can see here, just the I/O consumed just for this conversion or this transition from one code to another code, it can consume 100% of the cluster I/O for several days at a time. So which is clearly prohibitive cost of conversion for a system that is running, right? So this interferes with the foreground traffic. So thus a key barrier for realizing the substantial savings that redundancy tuning can provide is being able to do resource efficient conversion of erasure coded data. So take a small break here to answer any questions if there are so far, before moving on to addressing and studying this problem further.
Are there any questions?
So, Emily, I'm not monitoring the chat here. So, in case there are any questions,
I am
on the chat.
So,
yes,
please feel free to ask. I just want to then take the opportunity to say that tuning redundancy in coding is very hard. And in digital communications, we fix this K and N, but whenever, and we design a code with certain expectation in mind. And whenever things change, we are either overdoing it, coding too much, or we are not coding enough. And when it's digital, that means that if you're not coding enough, that everything is bad, the degradation is bad. And some of us have worked, some of us in this Zoom have worked on incremental redundancy hybrid ARQ. It's not identical, but it's enough for us to appreciate how important and actually hard this problem is. And I don't know whether other students have enough background. That's why I wanted to say a few words about that.
Thank you, Amina. Yeah, absolutely. So this turns out to be a very challenging problem, and just re-encoding is the default approach. And as we see here, it's prohibitive in cost. So we need a better solution. Right? So now moving on here. So there have been several works in the past that have considered specific cases and variants of this code conversion problem. And many of these are in the context of what is called as regenerating codes, which focuses on another problem called as a repair problem in coding, which basically means that, so when we have these code words with encode symbols, so repair problem corresponds to the problem of reconstructing, that is decoding only a small subset of these code word symbols, that is not decoding the entire data, but only, for example, one or two code symbols that are missing, and how one can do that more efficiently. Now, specifically for the code conversion problem, if we fix if k is fixed and only n needs to be changed, it can be considered as, that is, it can be mapped into a repair problem, and then regenerating codes, framework, and solutions can be used for that. However, in this work, we will be primarily focusing on studying the general framework for code conversion, that is going from any N1, K1, next, I will be using a theoretical framework for studying. So now in this code conversion problem, basically we want to convert data into data that is encoded under an NFKF. So these are the parameters of the final code, let's say CF. So we want to go from initial configuration to final configuration. And both codes are over the same, the modular arithmetic alphabet. So the alphabets are the same and the arithmetic is the same. And same information, that is the same message symbols, are stored in the initial and final configuration, but just that the encoding is different, right? So we want to move from one way of encoding into another. Now, in any framework for studying code conversion, the first thing we need to be able to handle is this change in the dimension, that is changing this parameter k, that is ki to kf. Now, in order to accommodate this, so we start with an LCM of ki and kf number of message symbols. That is, we start with a set of message symbols which can be the same message symbols in both the initial and the final configurations. Okay, so which would, let me denote it by capital M. So this is the LCM between ki and kf. Now, observe that since we have the same set of message symbols in both the initial and final configurations, but the dimension, that the parameter k is different, conversion process takes multiple code words in the initial configuration into multiple code words in the final configuration. So this need for considering multiple code words to capture the simplest instance of the problem is different, and it deviates from the existing literature on coding for storage systems, because in other problems, in coding for storage systems, like the repair problem that I was mentioning, and the regenerating codes framework, and also there are other problems, for example, local repair and so on, where a single code word is sufficient to capture the problem. But here we need to necessarily consider multiple code words in order to capture the problem. Okay, so now we have an NIKI code going to an NFKF code. So pictorially, it would look something like this. So we have the initial configuration. So recall this picture that we had seen earlier, right? So we had N code words. Now, since this is initial, we have NI and KI, and we have multiple different code words. And how many code words we will have would be precisely the number of message symbols M divided by KI, which is the dimension, because each code word will take KI message symbols. Right? So similarly, final configuration also will have multiple code words, but now the number of those code words would be different. It would be M over KF now, because the final dimension is KF. So this would be a good picture to keep in mind of what is happening in code conversion, because we're taking multiple initial code words into multiple final code words, where each of these two initial and final configurations are encoded in different codes. Okay, so now, since we have multiple code words, we need to specify how the message symbols are divided or associated with these different code words. So this is where we need to have some partitions. So we have to need partition functions, which we will denote by PI and PF. So we will have two partition functions, initial partition and final partition, which basically maps the message symbols into corresponding code words. So let me take an example to make this concrete. So suppose we want to go from a 3-2 code data encoded with a 3-2 code CI to a 5-3 code CF. So first we take LCM of KI and KF, that is 2 and 3 number of message symbols, right? So that is 6. So we have these 6 message symbols, A to F. Now the initial partition could be AB together, initial code K value is 2, right? So we combine 2 message symbols together and encode. And the final partition could be something like this. So ABC together and DEF together, because the final code has dimension 3. So pictorially, for this example, it would look something like this. So we have one initial code word encoding A and B, the second one is C and D, the third one encoding E and F, and each one of them have the corresponding parity symbol. And then after conversion, we want to go to a configuration which looks like this, where we have only 2 code words, and the first one encodes ABC together, and the second one encodes DEF together, and they have their corresponding parity symbols. Okay, so now with that concrete example, let's define what is a convertible codes. So a NIKI NFKF convertible code is defined as follows, and it consists of first a pair of codes CI and CF, which is what we want to CI, what we want to move from, that is from CI to data encoded under CF, and a pair of partitions, as we just saw, PI and PF, which will map how message symbols are associated with different code words, and a conversion procedure, which we'll denote by T, which will specify exactly how data gets converted from CI to CF. Now, the cost of the conversion procedure would be the cost of the conversion itself. So this conversion procedure T, so what is the cost of T would define the cost of conversion. Okay. So now the goal in designing a convertible code would be to design such as to minimize the cost of conversion. And what are the things that we can design? Are the codes CI and CF, the partition functions PI and PF, and the conversion procedure T. And we want to design these composites of the convertible codes framework so as to minimize the cost of conversion, given the parameters NIKA and NFKF. And in addition, we need to keep decodability constraints in mind. And this design has to be subject to desired decodability constraints on both CI and CF, because at different instances in time, data would be encoded with the code CI and CF. Okay? And for example, a decodability constraint that we saw earlier was this maximum distance separable, or MDS property, which was basically any K out of these N code symbols are sufficient to decode. Right? So that is one of the decodability constraints, for example, that we will consider and is very commonly used in storage systems. Now, there are various metrics to measure the cost of conversion. For example, based on different resources it will consume, right? So for example, the access cost, that is how many nodes get touched during the code conversion process, and the network bandwidth, which is basically the amount of data transfer that happens, the disk IO, that is how amount of data that is read or written from the disks, and CPU, and so on. So this is a wide design space, and in this talk, I'll be focusing only on one portion of this design space, where we will consider both initial and final codes being linear and MDS. So recall that linear codes are just where the functions are linear functions, right? The parity functions are linear functions of the data set. And the cost metrics that I'll focus today would be 2 of them. One would be the access cost, which is the number of nodes affected, either by reads or write for the process of conversion, and the bandwidth cost, which is the total amount of data transferred for conversion. And in the interest of time, I'll also limit only to a specific type of conversions called as the merge regime conversions. And this corresponds to combining multiple initial code words into a single final code word. So in terms of the parameters, you can think of it as KF being some integer multiple of KI. So recall that KF is the dimension of the final code and KI is the dimension of the initial code. And this integer multiple lambda would be basically the number of initial code words that are combined. And the ni and nf parameters can be arbitrary. So pictorially, this would look something like this. So this is the same definition of the merge regime that we just saw in the previous slide. I've kept it here for your reference. Now, pictorially, this would look something like this. So we start with this initial configuration with lambda code words. Each code word is for data encoded with this NIKI initial code CI. Now, because we're focusing on this merge regime, now the final configuration would just have a single code word with KF being lambda KI and NF is the parameter N, which is the length of the code for the final code. So pictorially, it would look like this, starting from multiple initial code words going into one code word. So merge regime plays an important role in covering the entire design space, but I'll not be going into the general parameter regimes in that talk. Okay, so we'll be focusing on linear MDS codes, access and bandwidth cost, specifically for the merge regime. Okay, so let's get into it. First, I'll focus on the access cost of conversion. Access cost corresponds to the number of nodes that are affected either by reads or by writes during conversion. So basically, we need to look at how many code symbols are read from the initial code words and how many code symbols are returned to the final code word. So this access cost is an important cost during conversion because it corresponds to how many disks are disturbed. Basically, how many disks are involved during the conversion process, because then all the foreground traffic that goes to those disks will be affected by the conversion process, right? So that's why this access cost is an important cost to measure. So access cost is basically now the summation of these two terms. One is the number of symbols read from the initial code words, which is the read cost, and plus the number of symbols written to the final code words, which is the write cost. Now let's get into the results. So first I'll talk about the lower bound on the access cost. So I'll introduce an additional parameter here, the parameter R, which is basically n minus k. Right? So we will have two of them for the initial and the final configuration. So we have Ri, which is ni minus ki, and Rf, which is nf minus kf. So an intuitive way of understanding what this R parameter corresponds to is to think about systematic codes. So in systematic codes, recall that out of n, k of them are original message symbols, right? So n minus k then corresponds to the number of parity symbols. So basically this R corresponds to the number of parity symbols in a code word. The results that I'm going to present are applicable for general codes, doesn't have to be systematic, but keeping systematic codes in mind makes it more intuitive and easier to understand and analyze the results. So you can keep systematic codes in mind when thinking about these results. Okay, so let's first consider the case where R is less than or equal to K, that is Ri is less than or equal to Ki. So the results naturally extend to the other case as well, as I will mention later, but we'll start with this. Okay, so we have Ri and Rf as defined, and Ri is less than or equal to Ki. This is the case we'll look at first. Okay? And at the bottom of these slides that I'm going to present, so I'll have this picture, which basically shows the different regimes that will come up in the result, and it will help us to visualize the results pictorially. Okay, so I'll keep pointing to this figure as we discuss the result. Here is the theorem. For all linear MDS convertible codes in the merge regime, if Rf is less than or equal to Ri, that is in this plot, this is the line for Rf. So when Rf is in this regime, that is when Rf is less than or equal to Ri, then access cost is greater than or equal to, so remember this is a lower bound, so the access cost is greater than or equal to summation of these two terms. The first term now here is the read cost. So with lambda times Rf, so recall the merge regime, we are combining lambda initial code words together, right? So this lambda times Rf basically corresponds to reading Rf symbols from each of the initial code words. Okay. And the second term is the write cost, which is basically writing new symbols, which is exactly RF. So if one were to use the default approach of re-encoding, then you will have to read KI, which is basically all the message symbols from the initial code word. So we will do a comparison from that, but something to keep in mind. Okay, so this was the regime where RF is less than or equal to RI. Now, when RF is greater than or equal to RI, that is in this brown regime, the access cost is lower bounded, that is, it has to be greater than or equal to lambda Ki plus RF. So this is an interesting regime because this is exactly the same as the default approach cost. So because look, the read cost here is basically Ki from each of the initial code words, right? You're reading all the message symbols. You can just decode the original message symbols, create the new parities, which is RF, and then write them, right? So this is the same as the default approach. So basically, in this case, no benefit is possible, but in the first case, it's better than the default approach. So instead of Ki, you have RF here, right? So, and we are looking at RF less than or equal to RI, and recall we are in the regime where RI is less than or equal to Ki. So basically, this is the regime where you can do better than the default approach. And this brown regime is the regime where you cannot do better than the default approach because the lower bound is exactly same as what default approach provides. Okay, so now let's just get rid of this assumption that we had that Ri is less than or equal to Ki. So the only thing that changes is now we will need to have two of these figures. So now one case where Ri is less than or equal to Ki and another case where Ki is less than or equal to Ri. The result remains similar. So for all MDS linear convertible codes in the merge regime, now the first condition becomes RF less than or equal to min of these two parameters instead of just having one of them. The lower bound remains the same and the other regime also remains the same. So the only change is in this term. Okay, so now this was the lower bound on the access cost. And at a very high level, I would like to just talk about how does this optimal solutions for this look like. And for that, we'll introduce a few additional terms, and we will keep this picture in mind when introducing these terms. So we have this initial configuration, the final configuration. We will call some symbols as unchanged symbols. And basically what it means is these are the symbols that remain intact in the initial configuration and the final configurations. That is, they remain identical, they don't change. So basically, you don't need to do anything for them. These are unchanged symbols. So here, these symbols which are mapped. So they would be in different initial code words and they could be mapped into different final code words, but they are the same symbols, they don't change. And some of them are what are called as retired symbols. And we're calling them retired symbols because those are the symbols from the initial code words, that's initial configurations, which will no longer be there in the final configuration. Okay, so, and these are the ones in this pictorially depicted in this figure, it is shown here. And some of them are new symbols, and new symbols are the ones in the final configuration. So these are the symbols which are not there in the initial configuration, but are there in the final configuration. Okay, so we have unchanged symbols, retired symbols, and new symbols. Now, how do optimal solutions look like? So here is a proposition. Now, in any linear MDS convertible code in the merged regime, there can be at most Ki unchanged symbols from each initial code word. So basically, at most Ki of them can change. Now, using this, we define something called as a stable convertible codes. So basically, stable convertible codes are ones in which exactly Ki of them change. So basically, since we have lambda initial code words, exactly lambda Ki unchanged symbols are there. And since recall that Ki are the original number of message symbols, right? So basically we have exactly RF new symbols. Okay, so RF new symbols and lambda Ki unchanged symbols. Now here is a result on how the optimal solutions look like. All access optimal linear MDS convertible codes in the merged regime are stable. That is basically any convertible codes that is in a merged regime is access optimal and it is linear and MDS, then it exactly has Ki number of unchanged symbols from each of the initial code words and exactly has RF new symbols. Okay, so this gives some idea and intuition into how the optimal solutions look like. And based on this, we have achievability results. So far we looked at only the lower box, right? And the achievability result is via an explicit construction. And it's a construction which is systematic and it exists for all merged regime parameters. So first case is a very simple one. So recall the two categories we had in the result, right? So one of them was the same as the default approach. So that case is trivial because you can just use the default approach and any linear MDS code would suffice. Now, the other case is the interesting one, which is where we could do better than the default approach. So now here, let's recall from the primer, the recap of Erasure codes that we had seen, that for linear codes, they can be represented using a matrix called a generator matrix. And when the code is systematic, because the first K symbols are exactly same as the message symbols, it will be an identity matrix, right? So this is I here, and there is a P matrix which specifies the parities. So we have GI and GF, which are generator matrices for the initial and the final codes. So now the construction, so in the interest of time, I will not go into the specific details, but I'll mention it at a very high level. So first, we present some structural properties that these generator matrices need to satisfy in order to first satisfy the MDS property. And this is a well-known result. It's called superregularity. Basically, if the codes have to be MDS, then these parity matrices, P, for both the initial and the final codes need to be superregular. It just means that every square submatrix of P needs to be non-singular. So basically, PI and PF need to be superregular just to be MDS. This is a very well-known result. Now, next property is the one that relates to code conversion, and we call this as a T-column block constructible. So what does this mean? So we say that an n by m1 matrix m1 is T-column constructible from n by m2 matrix m2. So I've shown the two pictures here. So we have m1 here and m2 here. So note that both of these are of the same height. So both are n by something, m1 and m2. And we say m1 is T-column constructible from m2 if there exists a subset of columns from m2 that span the columns of m1. Okay, so basically we can pick some columns from m2 and they will span all the columns of m1. Now, using this property, we build on top of it to what is called a T-column block constructible. And now we have two matrices m1 and m2, where m1 now has become taller. So it has exactly lambda times taller. So we have lambda n times m1 and this matrix m2. And now we will say this tall matrix m1 is T-column block constructible from m2 if and only if every submatrix, which is basically of the height n, exactly same as m2, and as specified here, which is basically starting from the top, you divide it exactly to the height of m2, and each one of them is T-column constructible, which was the previous property that we just saw. Okay, and then note that this is constructed in a specific way, which is exactly lambda times. Okay, so basically you can take some T columns from M2 and span the columns of each of these submatrices of M1. Okay, so now how does this relate to code conversion? So how does it relate to the conversion cost? So recall that this property of optimal solutions, right? So all access optimal linear MDS convertible codes in the merge regime are necessarily stable. And what that meant was it has exactly RF new symbols, and the read cost was RF from each of the initial code words, right? So basically, again, I don't have the theorem here, but if you recall the lower bound, it was lambda times RF, reading RF from each one of them. So basically, you're reading RF from each one of them. So basically, what that means is if it is sufficient, if the final parity matrix PF is RF column block constructible from PI. Okay, so basically, we want to have PF and PI of this form. So we have lambda times KI times NF minus KF, and PI would be KI times this. And these details are not important, but basically now the M1 and M2 basically corresponds to the PF and PI, the parity matrices. So putting this all together, this theorem just says that, you know, if these two properties are satisfied, then the construction would be access optimal linear MDS convertible code in the merge regime. And now we have the achievability result by constructing a matrix exactly to satisfy these properties. Yeah, so I just wanted to show at a very high level how we construct these matrices. So this is using the PI and PF matrices are constructed using a specially structured triangular arrays called as Hankel form. Basically, it has this structure where, you know, the same element B2 and B3 comes like this in this kind of the right diagonal matrices, and it leads to a sequence of constructions, and it's a trade-off. So basically, as the field size increases, the parameter range covered also increases. So this is the low field size practical constructions, although we have the achievability results for all the regions. The details of the results are available in the publications, but I'll skip them here in the interest of time. Now, quickly to just go over another cost, which is the bandwidth cost of conversion. And the bandwidth cost corresponds to the amount of data that is transferred during conversion. Now, this is not just the number of nodes that are touched, but it also accounts for the amount of data transfer, which basically corresponds to the network bandwidth consumed during conversion. Okay, so basically this includes sum of two terms: data transferred from initial code words and data transferred to final code words. And pictorially, you can think about it this way. So we have these initial code words stored on different disks, and you transfer some data from them. And then this is like a central coordinator where the data is read to, and then some computation is performed, and the new symbols are calculated and they are written. Okay, so the conversion bandwidth is the sum of all this transfer that has happened. Now, in order to optimize for the conversion bandwidth, it turns out that we need to consider vector codes. So basically, vector codes correspond to codes where each of the code symbols are now a vector, let's say, of alpha number of subsymbols rather than just being one symbol. And this helps in reducing or optimizing for bandwidth, because now, since each code symbol is a vector, it allows us to transfer only a part of them, a subset of them. So you don't need to read the entire symbol. You can read like half a symbol, which means that now, since it's a vector, now you can transfer only some subset of the code symbols or some functions of them. But the total amount of data that is transferred is less than the total amount of data that is stored in each node. So vector codes are a powerful tool in designing codes for storage systems, and it has been used to optimize for update complexity and also for optimizing the repair bandwidth in the context of regenerating codes. And it turns out they are quite useful even for optimizing for conversion bandwidth. So in order to model the problem for studying conversion bandwidth, we model the conversion process as an information flow graph. Now, this is the same information flow graph, again, has been a powerful tool in the literature on designing codes for storage systems. So here, the source, all right, saying this information flow graph, right? So we have sources, different nodes, and sinks. The sources here, we have in this picture, we have 3 sources, S1, S2, S3. Each of them correspond to the message symbols of each of the initial code words. And then we have nodes corresponding to each of the initial code symbols. This is the initial code words, initial configuration. And the link between S1, these sources, SI, and the corresponding code symbol nodes is alpha, because recall this is a vector code and each code symbol is a vector of length alpha. Okay? And similarly, we have nodes corresponding to the final code words. And recall this notion of unchanged symbols, retired symbols, and the new symbols that we had seen a few slides ago. So the same concept is there here too. Like if some symbols are unchanged, that is, they're identical in the initial and the final code words. And some of them are retired, the ones that are shown here in orange, denoted by R subscript notation. And some of them are new in the final code words. These are the new symbols that are not there in the initial configuration. Okay, so now how does conversion takes place? Now, in order to model conversion, you have certain amount of data transfer from each of these initial code symbols to a central coordinator. And then the new symbols are computed and then returned down here. So one thing I want to note here is that the amount of data that is transferred from the initial code words to the central location is denoted here as beta of x, meaning that it is variable for each of the nodes. It's a different amount of data that is transferred. So these links are of varying capacities. So this again deviates from the literature on other information flow graphs in storage systems, like, for example, regenerating codes, because they're typically having uniform link capacities turns out to be sufficient to achieve optimality, whereas here we can show that it is necessary to go with variable link capacities. That is, if we impose uniformity constraint, then we are necessarily suboptimal. Okay, so now after this conversion, then there in terms of the sinks in this information flow graph, there are so these TIs are the sinks, and these sinks basically model the decodability constraint for the final code words. That is, by connecting to any K and downloading the alpha symbols from each one of them, these sinks need to be able to decode the original data. Okay, so and then this is the network flow. And then we can take the min cut and then use that to get lower bounds on the amount of data transfer. Now, the conversion bandwidth here is basically now the summation of all these terms, the amount of data read from these green nodes, which are unchanged nodes, amount of data that are read from the retired nodes, which are this orange term, and the amount of data that is written to the new nodes, which are these purple nodes. Okay, so and basically, a min-cut study on this information flow graph helps us in arriving at the lower bounds for bandwidth. So going over the lower bounds, as we saw in the access cost, and we will keep comparing the two costs when we look at this. So with the same set in the access cost, and the same type of figure I'll have at the bottom to pictorially see where we are in terms of parameters. Now here is the theorem. For all linear MDS convertible codes in the merged regime, and when we are in this regime of parameters, that is RF less than or equal to RI, the same thing that we had seen in the access cost, then the conversion bandwidth is lower bounded by this term. So again, we have the summation of two terms for read and write, and this is the read bandwidth, and the second term is the write bandwidth. So if you look at this a little bit carefully, this is actually identical to what we had seen in the access cost. There we had lambda RF plus RF, just that we didn't have the term alpha, because there we were not considering an alpha length vector, right? Now, just that here each code symbol was divided into alpha symbols, or you can think of it as an alpha length vector. So we just have an alpha multiplier here. So basically in this regime, access optimal convertible codes are also bandwidth optimal because the lower bounds for both of them are same. And then this is based on the achievability results, of course, but I'll go to that. Okay, now when we are in this regime where RF is in between Ri and Ki, that is in this blue regime, this is an interesting regime because now here, this bandwidth cost, that is the read bandwidth, is higher than the first regime in this first part, but it is lower than the access cost. Because recalling the access cost, everything, once RF was above Ri, everything was equal to the default approach. So no savings was possible. But here, in between Ri and Ki, savings is possible. So this is better than the default approach. And then when RF is greater than or equal to Ki is when it becomes same as the default approach. There is no benefits are possible. Okay, and then like as we saw in the access cost, this assumption can be relaxed, and the only thing that changes is in this condition. So I'll just not go into that detail. Now, in order to put all these things together and to pictorially see what this means, right, so I'll put this into a figure. So I'll introduce two additional parameters, Ri tilde and Rf tilde, because there are many parameters, and in order to show them in a picture, it helps to parameterize them differently. So let's consider Ri tilde as Ri by Ki and Rf tilde as Rf by Kf. And on the y-axis here is the relative savings in bandwidth and access cost. So it's basically the percentage savings as compared to the default approach, which will be denoted by rho. X-axis is this Rf tilde. Don't have to focus so much on the specifics here, but it's a reparameterization. And we will have one curve per different values of Ri tilde. Now for Ri tilde equal to 0.4, one of these values, for the blue curve. So basically the bandwidth cost is shown with the conversion bandwidth is shown with the solid line, and the conversion access cost is shown by this dashed line. So until this point, that is where we have Ri tilde equal to Rf tilde, both of them overlap. So this was the regime where access optimal convertible codes are also bandwidth optimal, where the lower bounds were the same. And then at this point, basically savings drops to 0. So recall that you cannot do better than the default approach, right? For the access, whereas savings in bandwidth is still possible. Now, again, for other values of Ri tilde, the plot looks similar, but the knee where this access cost drops to 0, whereas the bandwidth cost savings continues to be access cost savings. So the access cost doesn't drop to 0, access cost savings drops to 0. That is, you cannot do better than the default approach. That knee varies and it appears at different locations. Okay, so just one last point. We do have achievability results on the bandwidth side as well. And for basically the lower bound is achievable for all parameters in the merge regime. And this is based on an explicit construction based on what is called as a piggybacking framework, which is a framework for constructing vector codes. You start with multiple instances of an original scalar code and then build on top of it. And here we use access optimal convertible codes as the base codes and then add information from one instance to another using what are called as piggybacking functions to get conversion bandwidth optimal codes. I'll not have the time to go into the details of that. And the vector length is of interest because that corresponds to the complexity of the code, and that is equal to Rf. So it's not that bad. Okay, I will, in the interest of time, there is this one additional thing that I will skip that. And instead, I will go to just summarize the talk and just discuss open problems. So in summary, heterogeneity-aware redundancy tuning offers a potential for significant benefits and substantial savings in storage systems in terms of both storage cost and energy costs. However, resource-efficient conversion of coded data from one code to another code is a key barrier to realizing the savings in real-world systems. So I presented convertible codes, which is a general framework to study this problem of code conversion, and a class of codes that optimize for the conversion cost. And I talked about two specific metrics to measure the conversion cost, access and bandwidth. And I discussed about tight lower bounds on these costs for linear MDS codes in the merge regime and explicit optimal constructions that meet these lower bounds. So far, we have only scratched the surface of this problem of code conversion, and there are many open problems. This and also constructing practical low field size storage codes like repair locality, repair bandwidth, update complexity, among others. So with that, thank you very much for your attention, and I would be happy to answer any questions.
Thank you very much, Rashmi. And there is a question in chat, if you can open it.
Yes,
yeah.
Yeah, is there a centralized encoder for the conversion? Is it possible to consider modify codes like shortening or lengthening MDS code for the access metric? Fang Wei, very interesting question. Here we are considering there is a centralized node where the data is accessed or read, and then some computations are performed to re-encode and then sent. But you can also think of it as being done in a distributed fashion. There is one node transfers to another node, and then the computation is performed. So this assumption of having the centralized node was more to simplify the model. It doesn't affect the results as much. So that was the first question. And the second one is shortening or lengthening, right? So that's a very good question again. So shortening and lengthening corresponds to modifying a code that is there, right? So modifying one code into get another code, right? As I was mentioning earlier, if you keep the K fixed and if you just change N, then it can be considered as a specific, it can be viewed as a repair problem, and there are optimal methods that can be used to reduce the bandwidth cost specifically. And in terms of specifically shortening and lengthening, it corresponds to modifying the code, that is generating a new code, as opposed to changing the data that is already encoded using the code into data that is encoded under another code. So there's a subtle difference here. That is constructing a new code from another code, which is just saying, can we have a new parity function which is derived from an original parity function? So that is, that relates to shortening and lengthening. Whereas here, what we are saying is you have lots of data, petabytes of data encoded under one code. Now you want to change it to be as encoded under some other code. Now, how can we move from data that is encoded under one code into this other configuration efficiently? Right, so that is the code conversion problem. So there is a slight difference in what the problem that these are addressing. I'll just stop sharing so that I can see the names and things more
better, yeah.
More broadly.
Yeah, that was a very good question. I guess I just wanted to say that, for example, many of these problems in data storage started appearing because of, as Rashmi mentioned, these petabytes of data. This is huge. All of this, if we could use many classical techniques in coding theory if we didn't have to deal with that much data. We would just Reencode from scratch, right? And for people in the audience who are not in the coding theory, it's like you have to redesign your house, or let's say you have a library of books, and all of a sudden you want to change the redundancy, or the number of books goes down or up. And of course you can empty everything, all shelves, and then start from the beginning. But what we want to do here is rearrange certain things efficiently so that you achieve what you want to achieve. Right. And I don't want to carry this parallel too far, but the bandwidth would be how many of these books you have to carry, and the access would be in how many rooms you have to enter, or something like that. So it's not, even in the real life, it's not an easy thing to do. Any other questions?
How do data security comes into play?
Yeah, thank you. That's a very good question. So the security aspect is typically handled by encryption, right? So in fact, in these large-scale storage systems, even before data is handed over to a storage system to be stored, they are all encrypted beforehand. So if you recall the picture of, we had these data blocks and how they are stored, each of the blocks would be a blocks from a file which is already encoded. So it's like a part of an encoded file. And it's a very good point that you raised, though, is it does arise in some context. Like, for example, now you're reading data from different nodes into one node together, right? And their security aspect does come into picture, where the storage system administrators need to be careful about what that node is.
Or using some of the data blocks as they were in the previous iteration.
Yes.
Does it assume that security somehow remains similar so that the same encryption will work?
Yes. Yeah. Right. Yeah. Interesting. Thank you. Yeah.
So many hard problems, right? Difficult problems. Thank you so much.
Thank you. Thank you all for coming. Thank you very much, Emina, for the invitation.